Okay, so here's a video about 2.4, which is about the technical definition of limits. So here's a technical definition. We say that the limit as x goes to a of f of x is L. And by the way, that's how I read this. Once again, the limit as x goes to a of f of x equals L. Sometimes people also say x approaches a. And we think of this as x getting really close to a, of course. But so we say that if for every number epsilon greater than 0, there is some other number delta that's also greater than 0, such that this inequality implies this inequality. And remember what this implies arrow means. That means whenever this is true, this is also true. And one thing to try to break down about this definition is what's the deal with these absolute values and inequalities. As you notice, this involves the absolute value of x minus a, and then over here it involves the absolute value of f of x minus L. And in both cases, you're doing the absolute value of something minus something else. What that is, it's a way of expressing the absolute difference between two numbers. If I want to tell you how far apart two numbers are, in terms of like the distance between two numbers, I subtract them and take the absolute value because, well, this is a way where it doesn't matter which number is bigger. If I want to tell you the distance between two numbers, what I would do is I would take the bigger one minus the smaller one. But this is a formula that you don't have to know which one is bigger. If you take the smaller one minus the bigger one, this will just give you a negative answer, and then the absolute value makes it positive the way it's supposed to be. So what I'm getting at is the absolute value of x minus a, that's another way of just saying the distance between x and a as numbers. To say that that distance is smaller than delta, that means that x, once again, the distance from x to a is smaller than delta. In other words, here's another way of saying it in red underneath, that x is smaller than a plus delta, because if it was bigger than this, then the distance to a would be too much. The distance, if x was larger than this number, then the distance from x to a would be larger than delta, but we know it's not. Also, if x was smaller than this number, then the distance from x to a would be too much. So this is really just saying that x is in between two numbers. You can start at a and then go down by delta, or you can start at a and go up by delta, and x just has to be in between those two. It's within a distance of delta from a. By the way, of course, there's this other part of this inequality, the part that says this is greater than 0. Saying that this is greater than 0 is really just saying that x can't equal a. Like if x were equal to a, that would be the only way that this could be 0. Otherwise, it's always going to be positive because it's an absolute value of something. So this is really just saying that x is close to a, but it's not exactly a. And when I say close, how close do I mean? I mean a distance of delta. X is within a distance of delta from a, and it's not exactly equal to a. So it's close to a, but not exactly equal. And so that statement is supposed to imply this one, which I can translate similarly. Like this is just saying that the distance between these two numbers is smaller than epsilon, which would mean that f of x is between these two numbers, where you can start at L and go up by epsilon, or you can start at L and go down by epsilon, and f of x has to be in between those two. So once again, roughly speaking, this is just saying that whenever x is close to a, but not exactly a, whenever that's true, f of x is close to L. And I keep saying the word close. That's because we think of delta and epsilon as small numbers. Delta is the distance from x to a, so it's if that's small, then that's why I say x is close to a, and epsilon is the distance from f of x to L, and if that's small, I say f of x is close to L. That's why I keep using the word close here, because epsilon and delta are like small distances. That's the way we think of them. So what does this mean in practice? Let's talk about a simple example. So here's a limit, and probably this is believable to you. The limit as x approaches 1 of 2x plus 1 equals 3. And the reason why this should make sense, and this is a little bit dangerous to talk about, but I mean, really the logic is just, if I plug in 1, I got 2 times 1 plus 1, and that's 3. What I just said isn't really a proof that this limit is true, but that's definitely how we should be thinking of this. It's just that if I plugged in 1, I would get 3. But let's talk a bit more about this, because once again, this statement is more than just talking about what happens when you plug in 1. In fact, what this is really about is of course what happens when you plug in numbers that are close to 1. And it's a question of how close to 1 does x need to be in order to make this not exactly 3, but close to 3. More specifically, and this is sort of getting to the more practical matter, that there's questions on the online homework that are kind of similar to this. What can we say about specific values of epsilon? Because according to the definition, when we have a limit, it's supposed to be that for every epsilon, there exists some delta. So a question that you can be asked about this is to say, okay, what value of delta goes with this value of epsilon or that value of epsilon? So let's talk about that. For this limit, and say epsilon equals 1, what can we do? And for this one, I went ahead and drew a graph, and as you can see, I drew some weird red lines. I'll explain what those are about in just a second, but they're going to help us answer this question. So keep in mind what this means. Epsilon, in the definition, the role that plays is it's the distance between f of x and L, which is the supposed limit. Here, L is this number. L is 3. And so right now we're talking about how are we going to make f of x? And of course, this is f of x. How are we going to make f of x close to L, which is 3? And what do we mean by close? We mean a distance of epsilon, which is 1. F of x in the picture is the y-coordinate. Right? When we talk about f of x and we're looking at the graph, that we're talking about the y-coordinate. So I want the y-coordinate, maybe I have some room to write down here. What I want is I want f of x to be between L plus epsilon, so that would be 3 plus 1, and L minus epsilon, 3 minus 1. In other words, I want f of x to be in between 2 and 4. Now, hopefully we can see why I drew these lines in advance. So here's 3. Yeah, I don't want to write too close to this because we're gonna do something later, and this is a small part. So, right, in any case, here's 2 and here's 4 on the y-axis. And I want to talk about the part of the graph that's in between here and here. What delta is like telling us information about where x should be. So now I'm going to look at the x coordinates. And what we're really looking for, I'm looking for a range of x's such that if I just look at that range of x values and I look at the part of the graph that falls in between those two x values, that part of the graph always lands between these two y values. That's what this is really saying, that whenever x falls within a certain range, y also falls within a certain range. More specifically, this. And so let me label this. This right here is 0.5. Like this x coordinate that corresponds to y equals 2 here. This one here is 1.5. And in the middle, of course, this is 1. So the question is, how close does x need to be to a? And by the way, the value of a here, a is the number that x is approaching. So for us, x is 1. So the question is, how close to a, which is 1, does x need to be in order to fall in this vertical window? And a partial answer to that is x just needs to be in between 0.5 and 1.5. As long as x is in between here and here, I trace this up back to the graph and I see that y is in between here and here. In other words, the distance from 1 to x needs to be, well, it needs to be in between here and here, and these are each a distance of 0.5 away from 1, right? If I go 0.5 to the left, I get this. If I go 0.5 to the right, I get this. So after all that talking, that's what I'm going to write here. It's the distance between A and like the outer edge of this horizontal window that's guaranteeing that I stay in this vertical window. Okay. Let's talk about epsilon equals 0.1. That's very similar. Remember, epsilon it's like this distance that tells you the vertical window. The vertical window goes from L plus epsilon to L minus epsilon. And keep in mind, L is 3 and epsilon is 0.1. So if I want a y coordinate in between 3 plus 0.1, so here's a y coordinate of 3.1 and 3 minus 0.1, so then I go down by 0.1, so 2.9. And I guess 3 is in the middle, right? And so I draw this smaller vertical window, and then I look down at the values of x that fall within that window. And by the way, I'm just telling you these for the purposes of this problem. This one would be, let's see, here's 2, and sorry, barely have room for this, but this one is 2.05, this one is 1.95. So the question is, how far away from 2 are these numbers? And each of them is a distance of 0.05. This one is 0.05 more than 2. This one is 0.05 less than 2. So in other words, the distance for this window, like you're either going 0.05 to the right or 0.05 to the left. So I'm going to say 0.05 for delta. And so that's basically what you can do if you just have a picture to work with and you have specific values of epsilon. Let me talk real quick about what you can say for any epsilon greater than 0, because technically what we just did still isn't really a proof that the limit as x goes to 1 of 2x plus 1 equals 3. Sure, I told you a value of delta for this epsilon, and I told you a value of delta for that epsilon, but according to the definition, it's supposed to be that for every epsilon greater than 0, there exists some delta greater than 0. So giving you values of delta that correspond to two different values of epsilon doesn't cut it formally. If we want to really completely prove that this limit is true, I have to basically show that no matter what epsilon is, I can always find an appropriate delta. And I'm only going to really do this once. This is touching on definitely the harder side of calculus, and we're going to get past this in not too long. But I want to do this at least once. What can we say about any epsilon greater than 0? Well, I'm going to start with the statement that I want to be true, and then I'm going to figure out what would have to be true in order to make that true, roughly speaking. I'm going to take f of x minus L. F of x is 2x plus 1. L is 3. And I'm just going to go ahead and set that less than epsilon, because that's what I want to be true, right? That's what I want here. Now, logic is important. So let me write if and only if. All I'm going to do is I'm going to simplify this. And so this is if and only if statement. This is 2x minus 2 less than epsilon. I can pull a 2 out. 2 is a positive number, so it can come outside of the absolute value with no problem. If I pull a 2 out, I get absolute value of x minus 1 less than epsilon. And then now I start to realize something. Now I start to realize how close I am. Because what am I trying to get at here? I want to figure out what statement that looks like this would guarantee that this statement is true. And so let's talk about how this statement looks. This statement looks like I've got the absolute value of x minus a. For us, a is 1. And so when I see this, I start to get excited. I see the absolute value of x minus a, right? I know that that's important. So let me try to isolate that. I can divide by 2. This is just multiplying both sides by a half. Maybe I should be careful. This is an inequality, and I'm multiplying both sides by a number, but it's a positive number. I'm multiplying both sides by a half. So I was careful. I'm not making a mistake by doing this. I get absolute value of x minus 1 is less than epsilon over 2. Now, yeah, just a quick discussion of the logic here. These are all if and only if steps. I didn't do anything sort of questionable. According to the definition, we only need the logic to go this way. We just need that this implies this. And since I started backwards, like I started with this one, really we need the logic to go this way. I need this statement to imply these statements. And of course it does, because all of these are less than or equal to. But let me call your attention to something. Of course, in the definition, this has this extra requirement. It's not just absolute value of x minus a is less than delta. It also has to be greater than 0. And like that implies this. But that's really not an issue here. if the logic all if this implies this, which implies this, and which implies this, in other words, like we have all of these arrows going from right to left, then I can add additional assumptions here, and that the logic still goes this way. I can't just add additional assumptions here and have the logic go forward, but I can add additional assumptions and have the logic go backwards. In other words, this is just a long-winded way for me saying, if this is true, then this is true. And by the way, of course, this number is playing the role of delta here, right? This is absolute value of x minus a is in between 0 and delta. Here I've got absolute value of x minus 1 is in between 0 and this number, so this is my delta. In other words, this is saying that for delta, you can always just use epsilon over 2. And hey, look at what we did a minute ago. That's exactly what we did. For epsilon equals 1, we used 0.5. For 0.1, we used 0.05. Delta was half of epsilon in both cases. Okay. But that's like I said, that's probably the last time I'm going to quite do this, where we actually find a delta for every possible epsilon. It's important, and the truth is I don't think it's an exaggeration to say that there was like centuries of work that went into developing the techniques of showing that for every epsilon there exists a delta for all types of various functions f of x, because we just did a fairly easy function. This is just a linear function. The graph is just a line, and it's easy to draw these pictures, but you have to imagine that people had to do all of this work for every type of function, and it was a lot of work. And if you're a math major, then you will learn more about that eventually, but we don't talk too much about that in Calc 1. We kind of give you an idea or a flavor of what we're doing, and then after that we just sort of stand on the shoulders of giants and use what they did without talking that much about the details. But today is the day we're talking about the details. So I'm not going to get too crazy here. This isn't a terribly ugly function. It's not a straight line. It's just the square root of x. And we're not going to do like general epsilon. We're just going to do a couple of specific values of epsilon. And we're going to find appropriate values of delta. So let's do epsilon equals 1. So, what do I want? I'll say it this way, I want this, f of x to be in between L minus epsilon and L plus epsilon. F of x here is the square root of x, so I want f of x to be between, okay, what's L? L is this, so it's this plus epsilon and this minus epsilon. So 2 plus 1 would be 3, 2 minus 1 would be 1. Of course, what I wrote here visually, since I drew the graph, it's not really necessary to draw the graph to do this, but since I already did, that's like I'm drawing my vertical window and I don't really have enough room for the graph. If you go far enough to the right, the graph eventually goes above 3. So it's like I'm drawing this vertical window from y equals 1 to y equals 3, and then I'm asking, like, what horizontal window does x need to be in? And again, well, of course, again, the graph doesn't go far enough to the right, but that's okay. I can solve this with equations and inequalities. If you have positive numbers and an inequality, then you can square everything. This is like a note that I put in this bubble. If you have, well, I said positive, but it's actually true for non-negative, like they're allowed to be 0. So if you have two numbers that are greater than or equal to 0, and you have an inequality in between them, then you can say that's true if and only if this is true, where this is like if you had squared both sides. And of course, if this is just less than instead of less than or equal to, then this becomes less than instead of less than or equal to. It's important that these numbers be non-negative, by the way. You can't just square both sides of any inequality and have it be true. However, these are all positive numbers. 1's positive, 3's positive, and square root of x is in between those two, so it would have to be positive. So I am allowed to square everything. So x is between 1 and 9. So what do I really want? Like, this is sort of telling me like a horizontal, like a range of x's, like a window of x's. Like, of course, here's x equals 1. And that makes sense. Like in the picture, like this lines up with this on the graph. Like this is a point on the graph. And x equals 9. Of course, x equals 9 is if I drew this graph going far enough to the right, at x equals 9, we would see that this graph crosses this line. But what do I really want for my final answer? I need to translate this into this type of statement. So there needs to be absolute values involved, but before that, let me talk about like subtracting a. What is a here? A would be 4. A is the number that x is approaching. So what if I just subtract 4 from everything? That's something I'm allowed to do. So x minus 4 is in between -3 and 5. Now let's talk about how to put the absolute values on. And what do we need to be true? Keep in mind, I only need this. According to the definition, I need this to imply this. And I'm doing this a bit backwards because I started with this statement, and then I'm going to end with this statement. So here the arrow's going forward, but here the way I'm writing it, I need this to go backward. And how does this need to look? First of all, I can put 0 here. That never hurts. Putting additional assumptions here never hurts the fact that this will imply going backwards. It never hurts to add additional assumptions if the statement you're adding the assumptions to is supposed to imply something else. The bigger question is, what number do I put here? Basically, this says that x minus 4 is in between -3 and 5, and I'm about to take the absolute value. So how can I guarantee that x minus 4 is going to be in between negative 3 and 5. What do I need to say about the distance between x and 4 in order to guarantee that x minus 4 is in between negative 3 and 5? I would say that the distance, if the distance is at most 3, then this has to be true. Let's go over that. If the distance from x to 4 is at most 3, then x minus 4, the smallest it could be is negative 3, and the largest it could be is positive 3. Right? That's what this means. This actually means that x minus 4 is in between negative 3 and positive 3. Why am I saying 3 instead of 5? Well, that's because that's literally what this says, that the absolute value of x minus 4 is less than 3. That just means if I take the absolute values off, that it's in between negative 3 and positive 3. Why is that okay? That's because if this number is in between negative 3 and positive 3, then of course it's in between negative 3 and 5. The window between negative 3 and positive 3 doesn't include anything outside of this. So let me make this easier. Again, there's a lot of talking because I'm trying to properly explain, but there's an easy way to figure out this 3. Oops. Once you get to this step, you can just take the absolute value of these two numbers, and whichever one's smaller, put that there. So this becomes 3, this is 5. I take the smaller of the two, and that's 3. So, right, let's do this again. Just with a different value of epsilon, and I'll go faster this time. I want square root of x to be, less than, greater than. So I'd go 2 minus 0.01 and then 2 plus 0.01. So this would be 1.99 and 2.01. I square everything, and I get 3.9601 less than x less than 4.0401. Okay, so I guess I was in the middle of this example and the video sort of cut off, but so sorry, it's like the rest of it is written already, but I'll explain it. So we had started with this, and then we squared both sides to get here, and then what I'm interested for this one is x minus 4, because remember x is going to 4 here, that's a. So once I get here, I'm going to subtract 4 from everything, so that way I have x minus 4 in the middle. And so I do this minus 4, and I get that number. I do this minus 4, I get that number. And then ultimately to get delta, once again, our strategy, just like the last time, is once I'm here, I'm going to take the minimum absolute value of this number, and that's delta. So I'm going to look at these two numbers, and whichever one has the smaller absolute value. So this one's absolute value would just be this without the negative sign, and this one would be, this is already positive, so the absolute value doesn't do anything. And the smaller of those two numbers would be this one. So delta is going to be positive 0.0399. Okay. And real quick, there was just another one that I was supposed to go through on this video. So this one is based purely off of a picture. We have no equation to go off of at all. We just have, well, on one like this, you just have to trust the graph that you're given. So here we see this sort of rectangle that's drawn. I see y equals 2 and y equals 2.3 and 1.7, and these horizontal lines sort of correspond to these vertical lines. So let's take a look at what we're doing. This claims that the limit as x goes to 3 of f of x equals 2. That goes with the picture. That's believable. Here's x equals 3. Here's y equals 2. And so I'm kind of looking at this point right here. And so it looks visually like the limit as x goes to 3 is 2. And what our job is to find a delta for epsilon equals 0.3. And the picture just is the picture contains all the information we need in order to do that. The limit is supposed to be 2, and we're doing epsilon is 0.3. So what you would do is you would start at 2, and then you would go up by epsilon and down by epsilon. So if I start at 2 and I go up by 0.3, then I'm here at 2.3. If I had gone down by 0.3 instead, I would be down at 1.7. And so like this is my vertical window for the graph. So I follow this across, and I see the corresponding x values, because now I trace these back down, and I see that as long as x is in this horizontal window between 2.8 and 3.3, for these values of x, when I look up, the graph stays between these two values of y. So that's what I start with, and I read this directly off of the picture. I'm just reading the 2.8 and the 3.3 right off of the picture. So I say, okay, what I want in order to stay in this vertical range is that I want x to stay in this horizontal range, and so that's what I write. And now I do the same trick where, once again, x is going to 3, so 3 is a, and I'm interested in the quantity x minus a. So once I'm here, I'm going to subtract 3 from everything, because that's a, and I get negative 0.2 here, I get 0.3 here, and as usual, delta is just going to be the minimum absolute value of these two numbers. So the absolute value of this one is 0.2, absolute value of this one is 0.3, the smaller of those is 0.2. So that's delta.